All right. I'm Sam Just. I'm a longtime Ceph contributor. Today I'm going to talk about a new kind of crush rule, which allows a bit more placement flexibility than the original algorithm, particularly for small EC clusters. So at least that's the killer use case. I'm going to try to avoid going into a ton of detail on how the algorithms work. Instead, I'm going to give some motivating examples and sort of walk you through the process step by step. So, but first, I got to give a little background on how normal crush works, maybe a little bit more than usual. So, for those of us who are not super familiar, crush is the algorithm we use to actually do data placement. It's the part that tells you where to actually find a particular object. So we take an object of name foo, in this case, we hash it to a 32-bit integer. We take that 32-bit integer, we truncate off most of the bits to get the placement ID in the specific pool you're actually trying to store the object in this case, pool 2. And then crucially, we take that and a specific OSD map, feed both of them to crush, and we get a mapping out. In this case, 248. So from that description, we don't need that much from crush. We need basically 3 things. 1, it needs to be deterministic. Given the same OSD map and the same placement group ID, we'd better always get the same answer. And we rely on this property to ensure that all OSDs and all clients all agree where a particular object should be at a particular epoch. If that ever breaks, pretty much everything breaks down. The second bit is balance. We need to respect the OSD weightings in the cluster map. This is pretty much how we deal with heterogeneously sized OSDs. You've all seen that in your crush maps, most likely. And then finally, and a little bit more subtly, we need stability. We need it to be the case that small changes in the map result in little bits of data movement. You can't add one OSD and suddenly find literally every object moving, although I know it can feel that way sometimes. So let's start with a fairly basic crush rule. Suppose you want to create an RBD pool configured with 3 replicas split across hosts. Relatively simple. We create a crush rule that just says take the root assigned to the SSD class, select 3 hosts, and then descend to a leaf. Yeah, so leaves famously being at the bottom of trees, we descend to them. So let's see how that plays out in practice. So consider the above crush hierarchy with a root containing 5 hosts, each of which has 8 OSDs for a grand total of 40. So the first step unconditionally populates the output with the root node. We then take that output, swap it as the input, and we start processing the next step, which is the important one in this rule. Step, CHOOSELEAF, first n type host. So the step part means it's a step. CHOOSELEAF is the type of step. First n is what distinguishes replicated rules from EC rules as a general rule. First n means that we don't care about order. In-depth means that we do. That's why with replicated pools, you never get those undefined OSDs in the middle of your acting set because we simply truncate them over. And then type host indicates the failure domain we're trying to split. So the first thing we do is we select host H1 and then immediately descend to an OSD for OSD 12. Same thing with host 0, but in this case we get OSD 7. We got unlucky. We hit host H1 again. So this is a normal property of Ceph, and we call this, or with a crush, and we call this a collision. We notice because H1 is already in the outset. So every time we do one of these selections, we have to scan the outset to find collisions. So we skip it and try again. This time we get lucky and get H4 and OSD 44. Cool. So far, so easy. However, crush rules can actually have multiple steps. So why do we have a special step called CHOOSELEAF? Why not just use 2 different steps? One that chooses 3 hosts and one that chooses 1 OSD on each one. So most of this plays out pretty similarly. We start again by unconditionally populating the root. We then take host H1 again, but we don't descend to the root or to the leaf. We keep going. We get H0. Once again, we get H1, it's a collision, and we drop it for the same reason, it's already in the outset, H4. We then flip it again and proceed to the next step, where we get where we actually descend to the OSD level for each one of these inputs. So we start with H1. Oh, hang on, there we go. Get OSD 12, then 7, then 44. So quick note before I continue, generally switching from CHOOSELEAF to a sequence of choose steps will not yield the same mappings. If you do this on your own cluster, it will result in every object moving. So don't do that at home. Makes the explanation easier though. So far, it seems like the only difference is that CHOOSELEAF is depth first and that the pair of choose steps is breadth first. There's a much larger, more important difference though, which is really the point of this talk. What would happen if we marked one of the OSDs out? Let's say OSD 7. In the first case, we start at this step, we notice that it's out. And note, the fact that OSD 7 is out doesn't prevent us from trying to select it. Because of that stability property I mentioned before, we try as much as we can not to change the order of selections we make during crush. But we do notice when we do select it that it's out. And at that point, we continue on. We hit H1 again, which is again, not a coincidence. We don't want to change the order of selections we make because that would change other mappings too. We continue on to get OSD 44 from H4, but since we only have 2 replicas, we keep going and we get H3 and OSD 32. So if we'd selected indep instead, the outcome would have been similar, but we would have preserved the position of OSD 44 instead of moving it to the left. Other than that, the behavior is pretty analogous. Okay, so CHOOSELEAF handles an out OSD by retrying the entire step. What happens in the case with 2 choose steps? The problem is that we don't actually notice OSD 7 is marked out until the second step, the portion where we're actually doing choose first and 1 type OSD. And that's it. We're locked in. We're stuck with host H0. There's nothing we can do about it. So we'll select a different OSD on the same host, and that should be fine, right? Yeah, no. So the problem with that is that gradually, as OSDs become marked out on a host, the other OSDs on that host will get fuller, more so than the rest of the cluster. So once 4 out of 8 are marked out, they'll be at double the capacity of the other, or double the utilization of the other OSDs in the cluster. And most people don't run utilizations low enough to tolerate that. Worse, if we mark out all of the OSDs, the placement groups that map to that host will just be degraded until the host is reweighted to 0 or removed from the map completely. So CHOOSELEAF is essentially a sidestep to this problem by combining those 2 steps together so they can be retried. So that's a pretty good solution, at least for a lot of common configurations, but not all configurations. So this one's a little busy, but let's say that you wanted to do a really dense erasure-coded configuration on a relatively small cluster. Let's say we want to put an 8+6 code such that 3 hosts have 4 OSDs and 1 host has 2. That would give you the ability to tolerate an entire host plus an additional OSD failure. In order to do the same thing with replication with a min size of 2, and you shouldn't be running a min size of 1, you would need replication 4, which is a lot more expensive. An overhead of 4, oh, I didn't change the slide. It would actually be 4 because of the min size thing. So an overhead of 4.0 versus 1.75 with this code. Right. So this rule is almost what we want. It does the split correctly. As long as the cluster is healthy, we will get what I just described. It looks like this will place 16, but if you give it a size 14 pool, it'll just truncate off the last 2, giving you 2 on the last host. So we just need to make this behave like CHOOSELEAF in that we need it to be able to deal without OSDs by retrying the entire set of steps and not just the last one. And that's the purpose of these new MSR rules. So they look pretty similar with a few different changes in vocabulary simply to make the rule compiler happy, but the idea is pretty simple. So let's see how this works with a slightly smaller MSR rule. Instead of our 8+6 rule, this will be 2+2 because it's way easier to make slides for that. So rather than taking each step in turn, MSR rules essentially process an output index for all of the steps before moving on to the next index. MSR rules need a little bit more working space. They need one sized array for each step in the rule. In this case, that would be 2 because there are 2 steps, and they are pre-populated with a special value that means not populated yet. I'm using X for this here. So first, we select a host for we select a host for the first rule and put it in the first slot on the first rule's working space. We then immediately recurse and select output position 0 and 1, corresponding to H1, and we get 12 and 15. Unsurprisingly, we then recurse back or return back and select H3 with 2 more OSDs. So pretty simple. The real question is, though, how do we deal with an OSD that's been marked out? Let's say OSD 15. So in this case, we just keep going. We select H3 and our corresponding 2 OSDs, and we've got 3 out of 4. So what MSR rules do here differently from normal crush rules is we wrap back around and try again. So in this case, we selected host H4 and notice it goes in that second position in that first vector. But it would have been legal to select host H1. If we had, we would probably have gotten different OSD, which would also have worked. But some of the time, we'll get a different host. In fact, most of the time, which is what we want. So there's only one catch. That's not 2 hosts, we've got 3. So I would say, don't worry about it. 3 hosts is fine. So the key observation is that CHOOSELEAF is a very special snowflake. It only ever maps a single leaf to a single host, right? So if we get an out OSD, there's nothing else there. We don't have any other OSDs on that host. We can just retry. But with MSR, let's say we don't hit an out OSD until the 3rd of 4 mappings. Do we want to throw away the other 2? If we chose to do it that way, we wouldn't even be able to use a host with fewer than 4 OSDs in the case I described before. So as soon as you drop from 4 to 3, suddenly everything remaining on those OSDs would get mapped somewhere else. And that's not great. It means you just can't use hosts like that. We get lower utilization overall. It's just less good. So instead, we relax the restrictions slightly because the thing we actually want isn't 2 hosts. What we want is no more than 2 OSDs on any single host. And that's what we do here. So those internal bucket things are essentially lower bounds, and we place an upper bound on the total descendants of any specific host. So generally speaking, MSR is different in that it is depth first. For each output position, we descend to a leaf before proceeding on to the next position. We always retry all the way from root, and we're free to map more failure domains than specified. And retries happen after a complete pass. And the short answer for why we do it that way is that it makes it easier not to disturb the other mappings. If we'd selected H4 earlier, we'd run the risk of colliding with a subsequent selection, which would have a ripple effect and change other mappings too. So that's all I've got prepared. Does anyone have any questions? So the good news about Crush is that it's pretty much just like code. It doesn't actually depend very much on the cluster itself. As I described earlier, all Rados actually cares about is that it get deterministic mappings that pretty much behave right. It doesn't actually care about the internal details of Crush at all. So Crush can be tested rather exhaustively in unit test form. We're not so much interested in the overall Rados behavior because that part isn't really different. We're interested in making sure that when we get changes, the appropriate amount of data moves, and we can simulate all of that stuff by just creating OSD maps, mapping out all of the placement groups, and then just measuring which ones moved with different perturbations to the map. And yeah, part of this work was adding a bunch of new testing to original Crush and new testing to this as well. I forgot about this slide. So generally speaking, you shouldn't ever need to make one of these rules yourself. There's a new config crush OSDs per failure domain available when you're creating an erasure code profile, and that'll automatically generate it for you. If you're interested in more information, there's there's some high-level explanation of the more user-facing bits in the documentation, and I annotated the actual code in a lot more detail than the original Crush implementation. All of it. All of it. They have nothing in common. If you get lucky and a particular object happens to be in the same place, but there is absolutely no guarantee or even attempt to make that work. Theoretically, yeah, but you'd have to upmap essentially everything. If we were serious about making it possible to switch mappings like that, it would be something like we would make it so that there was a configurable threshold, so that a pool could have two different maps associated with it, such that like the bottom, however many placement groups get the new one, and the top ones get the old one, so you can increase it a few placement groups at a time. That's a real feature we could actually do. I deliberately didn't mention any of those because it makes the story a lot more complicated. So for those of you who aren't familiar, Crush has a lot of tunables that have changed the way it behaves over the years. In particular, it has several tunables related to how it deals with CHOOSELEAF, in particular, with how it deals with hitting an out OSD. Once upon a time, it actually had an optimization where it tried to place the out OSD back on the same host. I think for recovery optimization reasons, if the OSD is still alive, then you get to recover locally, sort of, but that's a pretty unusual case. So, and in pretty much every case where there's an actual failure, it's deliberately bad. MSR did gain 2 new tunables, but they're a little simpler. Yes, it will. So it deliberately sidesteps many of those problems, although it has similar ones. The collision detection is mechanically very similar. So there are 2 tunables, one that governs the total number of tries it'll attempt at all, and a second one that governs how it attempts retries when it hits a collision within a bucket. And that's because if you're let's say you only have 5 OSDs per host, but you want to select 4 of them, you need a fair number of retries to actually get 4 out of 5. So there is a tension there, but it doesn't apply to out OSDs at all. Out OSDs are always a full retry. So yeah, that's what I'm looking for. Come on. Oh, this is basically a small cluster detail. For large clusters, this is much less important because you wouldn't be trying to force that many OSDs onto the same host. Where's my slide? There it is. Here we go. So this is really the configuration that this is designed to address. It can also address other things. It's a relatively generalization. Sorry. But specifically in this small cluster case, you don't have the freedom to put all of these OSDs on different hosts because you only got 5 of them. Yeah, so you'd get an analogous property if you were trying to split across racks, but you only had 5 racks. Same deal. You just changed the rule slightly. What's that? If you just need 1 replica per failure domain, then CHOOSELEAF will work fine. The interesting case here is that you didn't want to put 1 OSD in a rack. You wanted to put 4 of them in a rack, but no more than 4. Does that make sense? So in that case, with normal Crush, you'd have to use a 2-step rule, and it won't be able to retry. So if you never anticipate losing a whole rack, even that's not a problem. Or if racks are so big that you're not worried about the imbalance caused by out OSDs always migrating back into the same rack. You might even like it that way. But there are use cases it doesn't address.